Good evening. It's 6 p.m. Eastern Standard Time. I'm Charles Schultz, and this is the Randomizer for March 3rd, 2022. It's a beautiful Thursday. And tonight we're going to discuss an interesting term, a simple term, repel. All right. So this is simple, but it has some interesting twists and turns. And we're going to describe why this simple act, repelling something, is responsible for the solidity of matter, among other things. And we're going to get into the details about how it works and why. Um, Before we get rolling on that, I'm going to encourage all of my viewers to go to the Universe Science Center or Schultz Laboratories websites, sign up, become a member, support our growth and what we're doing, explore our galleries, and share it with your friends. It's a lot of fun. We're adding more material, and we're doing one of the best jobs that's possible, and that's sharing knowledge and information with everybody. So become a part of what we're doing, help us grow, and let's get out there and make it happen. Remember, if they close the schools again, you've got a school right here, and it works anywhere on Earth. So here we go. Repel. What is it all about? So you take a magnet and another magnet, and you put the two north poles or two south poles together, and you push, and they repel. They fight back. There's nothing there, but some force is making them move apart. You can't see it. You can run your hand to the middle of it. It doesn't seem to affect you at all. But there definitely is something transferring force from one to the other. And many of us as kids have laid two magnets on a flat surface and pushed one and the other scoots away from it as if some magical thing is making it happen. And we can do that right here. I have a magnet laying right on this paper, and I have another magnet right here, and the poles line up, and when I push this magnet, that one moves away. Some force that we cannot see or feel is repelling the other magnet. So what is that? Well, it happens for a number of reasons, but we're going to get into the electromagnetic force and what it has to do with it, because that's the easiest way of explaining it. So everything is matter or energy in this universe, and it takes three things to make a universe fundamentally. There's the geometry of the universe itself, the dimensions. Think of it as the graph paper upon which reality is written. And then there is the information that is present. It describes the spin, the momentum, the movement, the type of particle. And then there is the energy itself, the stuff of which everything is made. So it takes three things to make a universe, and those are the three things. If you were going to build a universe, that's what you would need. Now, what has this got to do with momentum? Well, anything in motion has a certain amount of relative energy to something that's standing still. So if one of them is in movement and the other standing still, and the first were to strike the other, it would transfer its momentum or part of it to the other. And so you see a ball on a pool table strike another ball and make it move. Pretty cool. So that's momentum, and it is the transfer of movement from one to another, transfer of momentum. In our universe, there are many particles, force carriers, that transfer momentum from one thing to another. That's kind of interesting all in its own. When you have a charged particle, such as an electron, we say that it has an electrical charge. Yeah, it does. And there can be things with positive charges or negative charges, greater charges or lesser charges. But one very clear rule emerges. Things with the same charge repel each other, just like north poles of magnets repel other north poles, south poles repel other south poles. So like charges repel, and opposite charges attract. It's a very simple thing. Think of one as being uphill and one as being downhill, in a sense. So this is the fundamental. Any particle that has a charge is surrounded by a change in the space-time around it. And what it does is it causes the appearance of virtual photons. These are photons that could exist, but don't have the energy to make them real. Think of it as a template for a photon, the imagining of what that photon would be. Now, if you look at the universe with a magnifying glass and you get to a smaller and smaller and smaller scale, when you get down to a meter divided by 33 zeros, 10 to the 33rd, you get down to an area of space called Wheeler space. And Wheeler space is known for one specific thing. It is chaotic. If you think of a pot of water that isn't boiling and it has a smooth, unrippled surface, that's like normal space. If you turn on the heat and the water begins to boil, the surface is seething and pulsing and changing in form. That boiling randomness is what Wheeler space is like. So a meter divided by 10 with 34 zeros, 33 zeros after it, puts you down at the edge of Wheeler space. Now, what's important about this? Wheeler space is where quantum noise exists in the universe. This is where all the people looking for free energy are trying to get their energy from. And in some cases you can, but mostly not, because there's a cost for everything. So now, at Wheeler space, a funny thing occurs. Energy in tiny packages will appear and vanish at random all the time. And there's a simple rule, and it's called the uncertainty principle. And it is the more energy that appears, the shorter its lifespan will be. It has to be paid back because you got something for nothing, you got to pay the debt. And this usually happens in fractions of a second, so tiny they're almost impossible to measure. Now, this virtual photon field is surrounding an electron. And in that field, if these little packages of random energy appear, they can make a photon appear and be real for a tiny fraction of time. The lower the energy is, the longer that virtual photon can interact with the rest of the universe. The shorter the lifespan, the higher the energy, it doesn't interact so much. Here's the key. They originate from the electron's position in space. So very, very close to the electron, you can get some very energetic ones, and that's where the repulsion is strongest. Farther away, you get little weak ones, and they can interact very weakly with things. Now, if you've ever fired a pistol or a rifle, you know that when you fire, it ejects a small amount of lead, but it kicks back strongly. This recoil is important. When a charged particle has a random photon appear and materialize near it, the electron recoils as if it was shot from a gun, and the particle goes flying off carrying its momentum the other way. The amount of recoil and the amount of photon energy total zero. Here's another electron, and it's negatively charged. And this photon goes flying off, strikes the other electron. What happens? It's like a bullet striking a target. It recoils. Here's the net effect. This electron and this electron are both emitting virtual photons. If they strike the other electron, it makes them move away. So, and the closer they get, the harder they fight away from each other from these virtual photons. So electric charge is the ability of the space-time around a charged particle to emit a field of virtual photons. And the close ones are highly energetic and fight hard, and the weak ones last longer, but they don't have much influence. A single electron left to its own in an uncontrolled space with nothing around it will bounce around at random, and it looks like Brownian motion. If you've ever looked under a microscope at a particle in water, you see it dancing around as the water molecules strike it at random from all sides. This is very much like what happens with the Wheeler space, the little charges appearing from random fluctuations in the quantum void. This is what makes the electrons dance. But as the electron dances this way, a little photon goes that way. And if another electron is nearby, if it strikes it, it recoils. So this is what makes electrons repel each other. Now, why is this important? What does it have to do with solid objects? Well, let's say you have an atom, and an atom has a core that is positively charged, and it clothes itself with a field of electrons. So the outside of the atom is a layer of negative charge, and the inside is a positive charge. Now this is the cool part. Knowing that the electrons have orbits that are like the layers of an onion, not like little planetary orbits, the electron is kind of like a Nerf ball. It's squishy. It's like a foam ball. And another electron, the atom with the electrons around it is squishy. And another atom nearby is kind of squishy. And a funny thing happens. If you try to push two of them together, they may bond, but you can't shove them together very far because they fight back hard. That's why objects are solid. They're made of material, and all the atoms in them are clothed in clouds of electrons. And if you try to penetrate that field, the electrons in your finger fight back. And as hard as you push, you are not strong enough, and your finger's not durable enough to crush that matter any tighter than it can be. So that's what makes things solid. Electrons repelling each other. Now, there's a caveat to that. If you have an atom, you know the inside is positive and the outside is negative. The electrons are moving around all the time in their shells. And oddly, sometimes the electrons will allow the positive charge from the core to shine out, to peek through. This has an interesting effect. Atoms do attract each other because the negative shell of this atom sees the positive interior of that in a little bit. It's kind of like the light peeking through blinds that you're shaking. And this charge draws atoms together. This is called van der Waals forces. They want to be close. But once they get so close, they will do one of two things. They will either bond by sharing electrons in the outer shell, or they will repel each other, and they cannot be compressed any further. So this is the repelling effect, the repulsion effect of the electrostatic field and the magnetic field, which is similar. It is the bonding effect that takes matter and sticks it together into molecules or crystals, and it is the force that creates the solidity in matter. Now, as I said, there are other particles that can do this. Well, any particle that carries force, the weak nuclear force, the strong nuclear force, the electrostatic force, the magnetic force, these forces all can attract or repel in varying degrees and varying strengths, but every one of them does it by carrying momentum, the force of movement, the raw stuff of energy. And now you know. One force is different, however, and that's gravitation. Gravitation attracts only, and there's a reason for that. Gravitation is caused by mass, and mass dimples space-time down. And as it does that, the space around it responds by doing something very similar to the photon field around an electron. It emits negative momentum. Gravitons make mass recoil towards other mass because they're carrying negative momentum. Now imagine if you shot a gun and instead of kicking you back, it pulled you forward. It did exactly the opposite of what you expected. Think of it as a deficit of energy, not an actual shove of energy. And you'd be very close to understanding why gravitation works the way it does. If a particle emits a graviton, it moves in the same direction as the graviton. And if the graviton strikes another particle, it doesn't recoil it, it drags it forward. It is negative momentum. So that explains why gravity attracts only and not repel. Is it possible to make repulsive gravity? Maybe, but you know, it's actually far easier to use a force that is much stronger than gravity to move things in the other direction. And even the shining of a flashlight gives off some momentum that, if left to its own devices, would eventually make the flashlight move away in the other direction. This is the reason a device called the light sail or solar sail would work. Imagine a large silver reflector, a very thin, lightweight material suspended in space near the sun, and the light of the sun striking that reflector and bouncing off. Every photon that strikes it leaves a little bit of momentum on that light sail, and this can be pushed slowly but relentlessly and eventually can reach very sizable velocities without the use of fuel. Now, it's an incredibly inefficient way to do it, but it does work. And it's been suggested numerous times that if we were to have powerful lasers aimed at a light sail, we could push it up to very high velocities, even close to the speed of light, and deliver it in another solar system very rapidly. And this is true. They now have a thing called the StarWisp project, where they're looking at creating extremely small, think of them almost as drone spacecraft, with just a fraction of a gram of processing power and a reflector to act as its guiding and driving force, we could launch thousands of them into space, drive them with a huge solar mirror or a giant laser, and send them off to other star systems and get there in just a few years. So, repel, very simple idea, fundamental concept of physics, and something that explains why matter is solid. Many forces can do it, most will. Gravity is the only exception known so far. And I think it's a fascinating, simple explanation of what happens at the nuts and bolts level of physics. So it's all about momentum. Photons, gravitons, everything transfers momentum from one thing to another. And that's how things make other things move. Repel, simple term. Again, I want to encourage people to come to the Universe Science Center, schultzlaboratories.com or universesciencecenter.com. Sign up for our classes, join and become a supporting member, and help us grow. And my quotation for tonight is, "Though I speak with the tongues of men and angels, but have not love, I have become sounding brass or a clanging cymbal." And that's 1 Corinthians 13:1. What does it mean? It doesn't matter how sensible or clear or useful what you're saying is, if you don't have love or sympathy for the people you're speaking with, they'll hear nothing but an extremely irritating noise. Speak kindly. It goes a long way. If you want to speak to people, they may not like the message, but if you're kindly, you've planted a seed in their heart. So if anybody has any questions, the floor is open, and we'll go from there. And I see nothing's coming up in the chat window and nothing's coming forward. So I declare this one a success. This has been the Randomizer for the 3rd of March, 2022, concept repel. And thank you for being here tonight. I appreciate all the members and support, and I appreciate everybody watching. I want everybody to have a great night, enjoy your life, and as usual, make the world a better place. Thank you for showing up.